Hey everyone, and welcome. I am absolutely thrilled to have you here today. Okay, let's just dive right into this. Today, we are unpacking one of the most foundational, fascinating, and honestly widely used tools in the entire world of machine learning. It's called the K-nearest neighbors algorithm, or as you'll usually hear it called, KNN. Now, whether you realize it or not, this little algorithm is quietly working behind the scenes in so many of the digital tools you and I use every single day. In this explainer, we're going to strip away all that intimidating computer science jargon and look at exactly how it works from the ground up.
Here's our roadmap for today. We're going to cover 1. The power of your neighbors. 2. The core mechanics of KNN. 3. Measuring distance between points. 4. The bias-variance trade-off. And finally, 5. Applications and limitations.
To get us started, I want you to picture this. Imagine you're standing right in the middle of a completely unfamiliar city, and you're trying to figure out if you'll actually like a particular restaurant down the street. What do? Well, you'd probably ask the people around you, right? But specifically, you'd look for people who seem to have similar tastes to your own. If 5 nearby people with food preferences just like yours all absolutely rave about the place, you're going to trust their judgment.
That restaurant scenario? That is exactly how the K-nearest neighbors algorithm works, except it's making predictions about massive amounts of data instead of your dinner plans. The entire premise relies on one really simple age-old assumption: birds of a feather flock together. It assumes that things that are similar to each other are naturally going to exist close to one another in space.
Moving on to section 1, the power of your neighbors. Let's see how this builds into an actual machine learning model. How do we take that intuitive idea of asking people nearby for restaurant advice and actually turn it into a computer algorithm? All right, let's meet the star of the show. KNN is an algorithm that predicts an outcome by basically looking at the closest, most similar data points. But here's a funny quirk. You'll often hear data scientists jokingly refer to it as a lazy learner. So what does it actually mean for us? Well, it doesn't mean the algorithm is bad or broken. It just means it doesn't build some massive, complex mathematical model up front during its training phase. Instead, it literally just memorizes the entire training dataset and sits there. It waits. All the heavy lifting, all the intense calculating only happens at the exact moment you ask it a question or give it a new piece of data to predict.
Let's look at a fantastic, concrete example from our source material to really visualize this. I call it the sweet potato test. Imagine a two-dimensional graph right in front of you. On the bottom horizontal axis, you have sweetness. On the vertical side axis, you have crunchiness. Now, we plot a bunch of different foods on this graph. Next, we introduce a brand new, completely unclassified query point, a sweet potato. To figure out what on earth a sweet potato is, the algorithm looks at its nearest neighbors on that graph. Because the sweet potato physically lands right next to points that are labeled apples, green beans, and corn, the algorithm uses those nearby neighbors to confidently classify our sweet potato.
But wait a second. For the algorithm to know that those other dots are apples or green beans in the first place, it needs an answer key, right? Exactly. This is why KNN is a type of what we call supervised machine learning. Supervised learning simply means the algorithm is fed labeled training data. You are literally handing it the answers up front so we can memorize what neighborhood belongs to what specific category. Without those helpful labels, the sweet potato would just be sitting next to a bunch of random anonymous dots, and the algorithm wouldn't have a clue what to do.
Now, it's pretty cool because KNN can actually answer 2 entirely different types of questions for us. If you want to sort something into a discrete category, like deciding if an incoming email is spam or not spam, or if our sweet potato is a vegetable, KNN uses something called classification. It basically takes a simple majority vote from the nearest neighbors. But what if you want to predict a continuous number instead, like say estimating someone's exact weight based on their height? Then KNN uses regression. Instead of taking a vote, it just takes the average of the numerical values of those nearest neighbors to give you a highly accurate estimate. The underlying machinery is the exact same, only that very final math step changes.
Section 2. The core mechanics of KNN. Okay, so we've got the general concept down, but what is the computer actually doing step by step when a new data point drops into the neighborhood?
It boils down to a very strict 4-step process. First up, compute distance. The algorithm measures the physical space between your new, unknown point and every single other point it has in its memory. Second, sort distances. It takes all those measurements and ranks them from closest to farthest away. Third, select K neighbors. It picks the top K closest points, and hold that thought because we're going to talk about what K actually means in just a minute. And finally, step 4. It either takes a majority vote for categories or an average for numbers, just like we just talked about. Section 3.
measuring distance between points. Now, you might have caught that step 1 was compute distance, but how does a computer actually measure the distance between two dots on a graph? It turns out there are a few different ways to pull this off, and picking the right one is absolutely crucial. The absolute most common method is called Euclidean distance. Think of this as taking a physical, straight ruler and drawing a direct line between two dots on a piece of paper. It is the shortest, straightest possible path. Now, mathematically, it's calculated using the square root of the sum of squared differences, which, yeah, sounds intensely complex, but visually, just picture that straight ruler. This method works perfectly when all your data features are on similar scales and the relationships are relatively linear.
But what if you literally can't travel in a straight line? Enter Manhattan distance. This is also famously known as the taxicab or city block distance. Imagine you're driving a yellow cab right in the middle of Manhattan. You can't just drive diagonally through the skyscrapers. You have to navigate strictly along the grid-like city blocks, making 90-degree right-angle turns. Manhattan distance calculates the path specifically along these axes. It is incredibly useful when your data naturally resembles a grid, like coordinates on a chessboard, or when dealing with specific integer values.
Then we have two other really powerful metrics mentioned in our sources. First is Minkowski distance, which is basically an adjustable formula. It has a special parameter called p. If you set p to 1, boom, it becomes the Manhattan taxicab distance. If you set p to 2, it becomes the Euclidean ruler distance. It essentially gives data scientists a handy dial to tune the math. And finally, there's the Hamming distance. Now this one is entirely different. It's an overlap metric used mostly for binary strings or categorical data, like checking if a text string is different by just 1 or 2 letters. You can think of it like the algorithm playing a game of spot the differences.
So, just to lock this in our brains for a second, we've got our straight ruler for Euclidean, our taxicab for Manhattan, our adjustable formula dial for Minkowski, and our spot the difference logic for Hamming. Choosing the right one depends entirely on what kind of data you are feeding into the algorithm.
Section 4. The bias-variance trade-off. All right, we've talked a lot about the nearest neighbors part of KNN, but what about the letter K? Let's move on to a concept that really represents the ultimate mathematical tightrope walk in machine learning.
So K is what we call a hyperparameter. Put simply, it's a positive integer chosen by the human operator before they even hit run on the algorithm. And it dictates exactly how many neighbors the algorithm should look at. If k equals 1, the algorithm only looks at the single closest point. If k equals 5, it looks at the 5 closest points. Getting this specific number right is pretty much the secret sauce to making the entire algorithm actually work. Let's see what happens when we get it wrong. If you set k to 1, a very small number, the model becomes incredibly overly sensitive. It will literally capture every single erratic, noisy data point. In the biz, we call this high variance, or overfitting. It follows the training data so closely that it performs terribly when you show it new data. On the flip side, if you set k to a massive number, the model just ignores local patterns entirely. It smooths everything out way too much. We call this high bias, or underfitting. It's kind of like asking the entire population of a city for restaurant advice. The unique, amazing local gyms just get completely drowned out by the generic popular chains. So the goal here is finding the Goldilocks zone for K. Not too small, not too big. How do we do that? Data scientists use clever techniques like cross-validation and something called the elbow method. Basically, they systematically test the algorithm over and over again, starting with K equals 1, then K equals 2, then 3, and so on, and they plot the error rate on a chart. They are looking for the exact point where the error rate drops sharply and then stabilizes, which, on a line graph, actually looks just like a bent elbow. That optimal K at the elbow strikes the perfect balance between bias and variance.
Section 5. Applications and limitations. Okay, we understand the theory, we know the distance math, and we've got the hyperparameter tuning down. Let's bring this back to reality and look at where this actually shines in the real world, and, just as importantly, where it completely falls apart.
The real-world applications are genuinely staggering. When Netflix pops up and suggests a movie by saying, because you watch this you might like, they are using a similarity engine that's directly inspired by KNN. In healthcare, it's being used to compare patient symptoms and genetic markers against vast databases of historical cases to help predict diseases like cancer. It's heavily used in finance for stock market forecasting. It's even used for something called missing data imputation, which is basically a fancy way of saying if a massive dataset has blank spots, KNN can look at the surrounding data and make a highly educated guess to fill in the blanks.
But
as with all things, it has its limitations. First up, it is a massive memory hog. Because it's a lazy learner, remember, it has to store the entire dataset in its active memory. Second, that means its prediction speed can actually be really slow, because it has to calculate the distance to every single point right at the exact moment you ask it a question. Third, it suffers from a dramatic-sounding problem called the curse of dimensionality. If you give it too many features, like over 20 or 30 different variables, the math just breaks down because suddenly everything starts to look equally far away. Finally, it absolutely requires feature scaling. Think about it. If one feature is measured from 1 to 10 and another is measured from 1 to 10,000, that larger number is going to completely dominate the ruler's distance calculation. You have to normalize or scale the data so everything plays on a level field.
Well, we have covered a whole lot of ground today, from finding local restaurants to taxicab geometry, all the way to the bias variance trade-off. The K-nearest neighbors algorithm proves that sometimes the absolute most powerful computational solutions actually rely on the simplest of ideas, that similar things exist closely together. So I'm going to leave you with this final thought to ponder. The next time an app recommends the perfect product or a song you love or exactly the right movie to you, ask yourself just how much of your digital life is currently being shaped by your nearest neighbors. Thanks for joining me on this explainer. Keep learning, stay curious, and I'll see you all next time.